Yeah, welcome to Compass Friday. We have another seminar given to us via Zoom today by Jamie Meacham from Imperial College London. He is a final year PhD student working with Professor Pavel Berlov, who was here a few years ago and gave a seminar, which you can still watch on our YouTube channel. And so he's working on modeling buoyant particles in oceanic surface velocity fields, focused on Lagrangian simulations to model cluster formation. And the applications include microplastics, inertial particles, and reaction rates in biogeochemical models. And that's what he will talk about. And Jamie, you can begin to share your screen now.
Okay, is that working?
Yes, it's working well.
Perfect, thanks. So first of all, thanks for having me and giving me the opportunity to talk about my research. So, as just mentioned, I'm mostly interested in modeling buoyant particles in the ocean and predominantly how the dynamics of these particles differs from passive traces, the sort of standard passive traces. So just to go over some of the motivations and um, some of the observations behind this research. Um, so positively buoyant material in the ocean is observed to undergo this sort of settling behavior. And that can include material like microplastics, oil spills, floating ice, some biological populations. And the main point is that through buoyancy or some other kind of depth maintaining force, these materials resist vertical velocities in the ocean. And what that leads to is material that predominantly only follows horizontal currents in the ocean. And this leads to an effect where even in three-dimensional incompressible current, where you would expect a conservation of concentration along Lagrangian paths, you get this effect where there's surface convergence and surface divergence, which leads to the formation of clusters and voids. Uh, Understanding the processes behind this sort of cluster formation for understanding the potential for reactions between different materials in the ocean, because it can impact the mixing properties between, say, microplastic contaminants and plankton populations, for instance. So basically, the idea is that these kind of surface convergences can lead to spatial heterogeneity. And there's kind of a classic example here. On this right-hand side, we've got a picture of uh, ocean color measurements from satellite data showing on a mesoscale coherent vortex this kind of spiral pattern of heterogeneity. And this may be in some part caused by the clustering process. So my work is mostly based around running these clustering simulations. And the way that we do that, for the most part, is we take a velocity field and we introduce a bunch of Lagrangian particles and invect them in that velocity field. And then we just track the formation of clusters and voids of those particles. So this involves solving some kind of ordinary differential equation like this one here, where we have that the velocity of the particle is just equal to the fluid velocity. But the point is, because we're looking at buoyant material, this fluid velocity is actually only the horizontal surface components of the velocity, not the full three-dimensional velocity. So additionally, we can, the way that we kind of differ from a lot of Lagrangian studies that are done is also integrate an intrinsic concentration along the Lagrangian paths. So if you have if you have an incompressible velocity field and you have conservation of concentration along the Lagrangian paths, then this isn't really a sensible thing to do. But because we have these surface convergences, we also have a change in concentration along the Lagrangian paths. And so if you think about from the perspective of the conservation of mass of tracer along the Lagrangian paths, you end up with an equation like this, which is that the change in concentration is proportional to concentration multiplied by the divergence along the Lagrangian path. By solving this equation, we can actually construct a concentration field of floating tracer from these intrinsic values, rather than doing what has often been done before, which is, say, just advecting a huge number of particles in these velocity fields and then maybe counting the number of particles in some bins and then sort of evaluating a concentration that way. By doing it in a Lagrangian sense instead, what we end up with is far finer spatial resolution, and we actually make the best use of the preferential concentration of these Lagrangian paths. So when we're interested in the clustering process, the fact that our Lagrangian paths, these sort of particles are attracted to the clusters, means that as we evolve our clustering simulation, we get better resolution of the tiles. So when we look at this concentration equation that we're solving along Lagrangian paths, you might think that actually what we're really doing now is solving for the concentration field using some kind of method of characteristics. So why don't we just use an Eulerian method like is often done in, say, a biogeochemical model? But the problem with this is the clustering process is something that is generally only observed in Lagrangian models, because when you have these Eulerian models, you have to introduce some kind of diffusivity, like an eddy diffusivity, to stabilize the numerics of the model. And while this sort of preserves the bulk behavior of, say, tracer transport and momentum transport and all these types of things, what it does is it completely damps out the clustering process. And this is sort of related to the fact that when you have these diffusivities, you don't properly represent up gradient transport of material. And that's precisely the thing that we're looking at in these clustering models. So my talk today is about clustering in the quasi-geostrophic setting, so in a dynamically constrained velocity field. But we've done a lot of work in the past to sort of understand the sensitivities of clustering a floating tracer in kinematic velocity fields, because then when we have some better idea of the kind of resolutions we need, of the kind of treatment we need of this clustering process to get good results, then we can take those insights into the dynamic fields. So the way that we've done this is well, and the way that it's been done by others in the past is generally you can construct a Gaussian random field that looks something like turbulence. And then we can just introduce Lagrangian particles, these floating tracer particles, into this divergent Gaussian random field. And we can just observe the clustering process, and we can see how it's affected by different things. So the first thing that has been shown in these kinematic fields is that the Lagrangian metrics really are preferable, say, using these particle binning methods or using Eulerian methods. And that's because, first of all, because of the preferential concentration that I mentioned before, but also because if, say, for instance, we were to advect some Lagrangian particles in an incompressible field, when you use these particle binning methods, you might still observe some spurious clustering. It's kind of a subtle thing, but the behavior of these ensembles of particles is fundamentally different to the behavior of the concentration field. And that's because you're imposing some kind of arbitrary finite length scale for this bin scale, and that introduces some additional errors. So first thing that we found in these kinematic fields is that the clustering process is really sensitive to temporal resolution and to the representation of temporal correlations. And sort of the reason behind that is because if you think of one of these particles moving in a divergent velocity field, the amount that that particle has clustered, the amount that the concentration has increased over time, is directly related to the entire history of divergence that it's experienced. And so what that leads to is a process that's very sensitive to the representations of that temporal structure. Another thing that we observed was in an idealized biogeochemical model, we saw that when you include this clustering process in one of these models, you see that actually it completely changes the dynamic systems behavior of these models. So basically what that means is if you're thinking about parameterizing these kind of subgrid actions and how they impact reacting traces, what you find is actually you can't ignore this clustering process. So for instance, in a traditional eddy diffusivity parameterization, what you're essentially doing is neglecting all the upgradient transport. You're neglecting all the clustering. You're including everything as this kind of diffusive smoothing transport. And what that does is it neglects the mixing processes this clustering process can cause. So now that we have these kind of observations, we can start to move towards dynamically constrained fields, but with a methodology that we have that is motivated by sort of the observations we've made. And so just on the right hand here, on the top left, you can see this is the kind of concentration field that we've reconstructed from the Lagrangian particles. And it's quite small here. You'll see it in better detail for the quasigeostrophic model, but you can sort of see how by using this Lagrangian method, we've got all these very sharp concentration gradients that we wouldn't be able to resolve in a Eulerian model, for instance, because of the diffusivities. So, so we're moving to a dynamical field. We're moving towards quasigeostrophic ocean model, and then we're going to perform clustering studies in that. So we choose QG because it's sort of the simplest dynamical model that we can use that satisfies the requirements we have for a clustering simulation. So for clustering to occur, what we need is a divergence in the surface velocities. And so where this divergence arises in QG is from movements of so we've got a two-layer QG system. We have a shallow upper layer and a deep lower layer, and this is our idealized ocean that we're using as a model. And so this idealized ocean, the vertical velocities, so if you have a region of downwelling, then this is going to lead to surface convergence. If you think so that the full three-dimensional field is incompressible, but then if you have a floating tracer that doesn't follow the vertical velocities, then we have surface convergence. So, and then if we have a location of upwelling, we have surface divergence. So downwelling, we'll see clusters forming, and in upwelling, we'll see voids of floating tracer forming. So that vertical velocity in the two-layer QG system is provided by movements of the layer interface between the two layers, because we have a rigid lid at the top of the ocean, and we have a rigid lid at the bottom boundary as well. And where in QG, where this vertical velocity appears, is it appears at order 1 in the Rossby number expansion. So what that means is it's an ageostrophic effect, because the geostrophic currents themselves are not just three-dimensionally incompressible, they're also two-dimensionally incompressible. So if you follow through in the derivation of QG, what you find is that you get these ageostrophic divergences, which will be the source of our clustering, which are proportional to the rate of change of the depth of the layer interface. So basically, this vertical velocity. And the other thing that QG gives us is it's very easy for us to generate turbulent velocities in two-layer QG. We can simply impose a fixed background shear in the upper layer, and then basically the turbulence will be generated for us through baroclinic instability. So just to give you a view of what that simulation looks like. This is the upper layer stream function of our QG simulation. And what you can basically see is there's this sort of turbulent background to the solution. And so the way we generate turbulence is we run the simulation from rest for 1,500 days. And then to perform our clustering simulation, what we're going to do is we're going to take that turbulent velocity field that's developed and we're going to run it for another 260 days. But then motivated by the fact that we know the clustering process is very sensitive to these temporal correlations, we're going to take very fine half-day intervals to say this QG field, which we're then going to use in the advection of the floating tracer. So what you can see is this kind of this sort of weak turbulent background. And then on top of that, there's these very strong coherent vortices. And this is very typical of sort of two-dimensional quasigeostrophy. And on the left-hand side, we've got the evolution in an animation, and these red curves are the coherent vortices that have been detected through a Lagrangian coherent structure method, which I'll describe in a minute. But just to sort of talk a bit more about motion. On the right-hand side, we have some energy spectra. So this top left plot here is the energy spectrum from the simulation for the geostrophic, the ageostrophic, and the total velocity. The way that we get the ageostrophic velocity is we calculate the ageostrophic divergence from the geostrophic stream functions. And then what we do is we assume that that ageostrophic velocity is purely potential. And then we can invert that relationship to find the ageostrophic velocities. So essentially, in this QG setting, the ageostrophic velocities are entirely diagnosed by the geostrophic velocities. So what we can see in this energy spectrum is we see a typical turbulent energy spectrum for the geostrophic flow. But then what we also see is that there's sort of a peak at this deformation radius scale, which is 25 kilometers for the simulation, which is associated with the coherent vortices. Then as you go to smaller and smaller scales, less and less of this turbulent energy is contained at those scales. However, if we instead look at the ageostrophic velocity, which is this blue energy spectrum, what we see is that it's far more broadband. So there's far more energy contained at the smaller scales in this ageostrophic response, but this isn't including any higher order Rossby number effects. This is just the ageostrophic response to the geostrophic flow. So it's like the eddy pumping. If we go move to this middle plot, we can find a Rossby number as the root mean square of the ageostrophic velocity divided by the root mean square of the geostrophic velocity. And we basically see that what I said, the scales are dominated by geostrophic velocity. So now on the top right, because we've seen in clustering simulations before that these things are very sensitive to temporal correlations, we've not just done a spatial analysis of the energy spectrum, we've also done a frequency analysis. And basically the reason we've done this is to make sure that we're definitely resolving the necessary timescales in this clustering simulation. And what we can actually see is that we have the frequency spectrum for the geostrophic velocity, but then also for the ageostrophic divergence. And what we can see is that the ageostrophic divergence actually has more spectral power at the slower frequencies. And this might seem strange because the ageostrophic velocity is more concentrated at smaller spatial scales, but actually what it seems to be is that the ageostrophic divergence is a response to the large scale structures. So most vortices, not with the background turbulent flow. So these coherent vortices, we kind of anticipate that they'll be important in clustering because of this strong ageostrophic divergence. And these vortices are a natural consequence of QG dynamics, of particularly the inverse energy cascade. So in the turbulent flow, the entropy is moving downscale, but then the energy is moving upscale to larger and larger scales. And even though these coherent vortices take up a very small amount of the domain area, they contain them, like they contain most of the energy that's in the system. So in this particular case, the coherent vortices take up about 5% of the domain area. Once they form, they're incredibly stable, which, because of the importance of temporal coherence in the clustering process, that means we expect that these vortices will be important in clustering. And so a way to define these coherent vortices in a sensible way so that we can then detect them is in terms of their transport properties. So you can think of them as material loops which resist deformation over time, and then using these what are called Lagrangian Coherent Structure metrics, and there's loads to choose from. We can sort of detect these coherent vortices in an objective way and then track them over time. And then once we perform the clustering simulation, we can track the clusters inside these coherent vortices. So we chose to use Lagrangian Averaged Vorticity Deviation for our and this is for two reasons. One is because it's very easy to, so it's an objective metric, which means it's independent of your frame of reference, which is a very nice property. But then it's also very easy to calculate because it just involves, as I'll show in a second, integrating the vorticity along the Lagrangian paths. And it's also closely related to the QG dynamics, and that's a consequence of the fact that these coherent vortices, which are areas of very large vorticity, are also areas of large ageostrophic divergence. So we'll take our QG, we took our QG simulation, and the first thing we do is, instead of advecting particles in the full geostrophic and ageostrophic velocity, we advect them just in the geostrophic velocity. And then along those Lagrangian paths that result, we integrate the upper layer vorticity. And what this gives us is a field in terms of the initial conditions of the Lagrangian particles, which basically you can see in this right-hand side here, on the left-hand plot, we've got the Lagrangian average vorticity deviation for the full 260-day simulation. And you can see how, using this method, all of the background variability is smoothed out over time as we integrate this vorticity. And all that's left over is just the large buildup of vorticity inside the coherent vortices. And so then what we can do is we can define an objective Lagrangian vortex just using the contours of this Lagrangian average vorticity deviation field. And we do that and we find, well, exactly the boundaries that were in the previous animation. So then once we have the contours which define the vortex boundaries, we can then track them over time by just defining the boundary of the vortex as the material loop that's initialized at that contour. And so if we look at this plot B here, we can see the trajectories of each coherent vortex over the course of the simulation. And so each vortex here, for future reference, has been assigned an index according to how strong it is. So the strongest vortex is vortex 0, moving all the way up to vortex 14. And then in red here, these are the cyclones, and then in black are the anticyclones. And so part of the motivation behind using this particular solution is we have a nice mix of cyclones and anticyclones, and the move over a significant portion of the domain over the simulation. So now we'll finally do the clustering simulation, right? So now what we're going to do is, rather than just advecting the geostrophic velocity, we're going to take this potential ageostrophic velocity and we're going to advect the particles in the combined velocity field. So we use 60 million particles because when you have this clustering simulation and over time, your Lagrangian paths are going to be attracted towards the regions of intense clustering. And that means in other areas of the domain, you're going to lose resolution. So on the one hand, we like this because we want to resolve the clusters as well as possible. But on the other hand, we lose resolution in other parts of the domain. So we use a large number of particles to resolve as much as we can for as long a time as we can. So then what we do, so we've got these Lagrangian paths that follow both the geostrophic and ageostrophic velocity. And then the concentration along the Lagrangian path is then the same as this concentration equation I mentioned earlier with this ageostrophic divergence. So we can find the concentration along every Lagrangian path, and then we can construct the full concentration field from the ensemble of particles. And so next is what this simulation looks like after you've run it for some time. And on the left hand here, we've got the full domain area. So this is 3,600 by 3,600 kilometers. We've got all the coherent vortices in there. And then there's 4 selected vortices on the other side here. So looking at the full domain, you can see quite clearly these very bright spots with a very dark background field. So this is the concentration field, and basically what we're seeing here is the accumulation on the coherent vortices. There really is almost no clustering outside of these areas. It really is totally dominated by these vortices. And so what we have at the top here is we have vortex 0 and vortex 3, and these are chosen to show what the expected behavior of these floating traces is. So in a few previous studies, what's been observed and what's been quoted as like the general expectation is that cyclones will form clusters and anticyclones will form voids. So cyclones are attractive, the floating tracer, and anticyclones are repulsive. And this is actually what we see in the majority of cases for these coherent vortices. So this vortex 0, we can see the strong accumulation forming this spiral pattern as it just hoovers up the floating tracer in its orbit. Whereas for this anticyclones, vortex 3, what we see is that it expels material and we see the formation of a void with just a bit of material collected around the boundary. But the thing is, what we actually observe is that the relationship between clustering behavior and vortex sign is a bit more complicated. So on the bottom here, we have 2 examples where it actually defies this expectation. So if you look at vortex 6 here, you can see that initially it's actually voiding material, it's actually expelling material. It does end up as a cluster, but for the first part of its lifetime, it's actually expelling the floating tracer. Whereas for this anticyclone, we see the opposite. We see at first it's expelling tracer as you'd expect, but then as we get to the end of the simulation, it starts to attract floating material to its boundary and it starts to form a cluster. And so one thing we can do is we have the vortex boundary defined from this Lagrangian averaged vorticity deviation method. So then we can just count the number of particles that are inside this vortex at any one time, and then we can track the total mass of floating tracer that's inside each vortex. And so this is what we find. On the right-hand side, we have the total amount of floating tracer in each vortex normalized by what it was at the initial beginning of the simulation. So this is essentially like a concentration enhancement of floating tracer inside the coherent vortices. So the top 3 plots, you'll notice that the vortices aren't in order here, and that's because the top 3 plots are all the cyclones, and then the bottom plot is all the anticyclones. And so what we see is that generally the expected behavior holds, that generally cyclones cluster and generally anticyclones form voids, but it's slightly different in that you see that both anticyclones and cyclones can go through periods of expelling and attracting floating tracer. So what that kind of tells us is that the relationship between clustering and vortex sign is more complicated than you might initially expect. And actually, it's to do with the evolution of the coherent vortex, not just its sign. But also what we see is that there's just a huge difference in the amount of transport of this floating tracer compared to passive tracer. So you can see that for some of these cyclones, the density enhancement of floating tracer is between 10 and 100 times, which means that these coherent vortices are transporting hundreds of times more floating tracer than they would passive tracer. And that's kind of unexpected because we're still in a QG setting here. So we're in a very low Rossby number context. So the Rossby number for this simulation is about 0.01. So the ageostrophic velocities are 100 times smaller than the geostrophic velocities, and yet we're just because that divergence along the Lagrangian path can accumulate over time, we still see that there really is intense ageostrophic differences. So the other thing we can do is we can use these intrinsic concentrations that we've integrated along the Lagrangian paths, and we can define certain statistical metrics that will uncover some of the properties of this clustering process. So two very important ones are the cluster mass and area. The cluster mass is a measure of all the mass. So basically, both of these quantities have a reference concentration, and the cluster mass tells us how much mass of floating tracer is contained inside a C bar isoline. So that we have this reference concentration C bar, and then we have M, which is all the mass inside that isobar, inside that isoline. And then we also have the cluster area, which is a measure of how much area that is contained within that isoline as well. So in the kinematic fields, what we often observe is what's called exponential clustering. So we end up with a situation where no matter what reference concentration you choose, eventually all the mass is contained within that concentration isoline, and the area that those concentration isolines bound actually goes to zero. So what you end up with is these sort of infinitely dense, infinitely small clusters. And we see something quite similar even in this quasigeostrophic velocity field, although it's much slower, much more. It's not so. It doesn't asymptote to this sort of unphysical eventuality. So what we can also do is we can look at this same mass and area, but we can restrict them to the coherent vortices. So MV and SV. So MV is the cluster mass within a C-bar isoline, but then that's also within the coherent vortices. So we're integrating over all the positions inside the coherent vortices, as well as all the initial positions. So what this overlap tells us is how much of the clustering process is dominated by the coherent vortices. And if we perform that analysis, what we find is that it's very much dominated by coherent vortices. So here, what I have is the ratio of the cluster mass inside the vortices to the total cluster mass in the whole domain. And what you can see is actually for a significant amount of reference. So on the x-axis here, we have the time of the simulation in days, and on the y-axis, we have the reference concentration. So if I take a horizontal slice in this plot, what I'm finding is how much of the floating tracer that has clustered above C bar is inside the coherent vortices. And what we see is that for higher reference concentrations, the entirety of the floating tracer that's clustered above that value is contained inside these coherent vortices. And a very important point is we haven't even detected the coherent vortices that are forming as the simulation is running. We were only focused on the ones that existed at the point of initialization of the clustering simulation. So what that means is that these coherent vortices, they don't just dominate the clustering process, they also dominate for a very long time, even as more vortices form. And we can see that by the end of the simulation, even then, if you have a particle that's clustered above, say C bar equals 50, you've still got about 75% of the floating tracer inside the vortices. And this is surprising because, you know, these coherent vortices only take up 5% of the domain. So they really are very much overrepresenting the floating tracer content. So the mechanism behind this is, it seems like it's a combination of the coherence of these objects, but also the dynamics. So if we look at the flux of the ageostrophic velocity through these coherent boundaries, you can do a bit of a mathematical manipulation, and what you find is that this flux is related to the rate of change of vorticity inside the coherent vortex. So part of the reason why particularly why these Lagrangian average vorticity deviation coherent vortices are so good at picking out the regions of intense clustering is because they are associated with large vorticity and they're associated with large changes of vorticity. This also tells us a bit more about why we have this relationship with vortex sign. So basically, if we have a cyclonic vortex forming, then we have vorticity increasing because we have positive vorticity, and as the vortex gets stronger, it gets more and more positive. And that leads to void formation because we have an increase in vorticity, so this F is negative. Oh, sorry, this F is positive. So basically what we have is that cyclones, as they form, form voids, but then as they decay at the end of their life cycle, they cluster. And we have the opposite relationship for anticyclones. So for anticyclones, as they form clusters, and then as they decay, they form voids. So what we've actually observed in the simulation is sort of an accident of the initial conditions. Predominantly, most of the vortices that we're seeing in the simulation are decaying over the course of the simulation because we've specifically looked at the ones that were there at the beginning of the clustering simulation. So we're not looking at the ones that are actively forming. So then actually, even though we've observed that for the most part, cyclones cluster and anticyclones void, we're actually seeing only half of the behavior that they undergo over their lifetime. So just some of the observations. We have powerful fast clustering. So even though we're very low Rossby number, with very small ageostrophic divergence, we're seeing the formation of these really huge clusters, which kind of motivates the inclusion of these effects in other models. And I'll talk a bit about that in a second. But so the clustering is totally dominated by the strongest coherent structures. And that's interesting because these coherent structures are important even in passive tracer transport because they separate out the domain. So you end up seeing very coherent patterns in the passive tracer transport over time. But it seems like this effect is actually magnified in the case of floating tracer. So then we see that the relationship between clustering is deeply sort of related to the dynamics of these coherent vortices. It's not just a fact of temporal coherence. We also see that when you observe clustering in many models, it may actually be related to the initial conditions and not related to the actual dynamics. and sort of you have to be careful there in justifying the mechanisms behind clustering. We also see that resolving these voids for long times is very difficult. We need a lot of particles because they expel this floating tracer so quickly. So some future directions, we're mostly focused on very small materials, so things like microplastics or biological populations where you have very small particles that really do behave as passive tracer in the horizontal, in their horizontal advection. But if we were to consider particles that have some kind of finite inertia, so if we wanted to model, say, Lagrangian drifters or larger pieces of ocean flotsam, so larger pieces of debris and other things, then we need to look into inertial effects. And this has already been done in the past. You can look at the slow manifold of these inertial particles, and you can use the geostrophic scaling, and basically it was shown in a paper that essentially the added mass and the Coriolis force lead to clustering of inertial particles. But actually, in that case, this clustering was considered in an incompressible background fluid velocity, but seen how the ageostrophic velocity can still cause strong clustering. And actually, there's some sort of intermediate particle sizes where you get an interplay between these effects. And I have a few sort of preliminary results to show you on the next slide. So the next thing is, how does clustering affect the sort of biogeochemical forces inside these vortices? Is it technically a significant effect that can't be resolved in current biogeochemical models because they're not eddy resolving? And because they're Eulerian models, they have this very strong eddy diffusivity, which preventing this impact of the efficient mixing. Next is, so we have this quasi-geostrophic framework, and that means that we have clustering due to eddy pumping, due to the movement of the middle layer interface as these vortices form and decay. But this obviously, in reality, isn't the only source of surface convergence and divergence. Two important ones. So first of all, the Ekman currents. So the Ekman currents aren't considered here because there's no wind forcing. Our turbulence is forced by baroclinic instability. But Ekman currents are potentially very important for clustering. And then also inertial gravity waves, which obviously are filtered out in a quasi-geostrophic system, but are expected to be very important for clustering. Then we can sort of start to think about how do the observations we've seen in this model, what do they mean for more realistic settings? For instance, if you think of these anticyclones, as they form, they're going to hoover up material around them. And then as they decay, they're going to expel it. So what does that mean for something, say, in the boundary current? So for instance, in the Agoulos current, where you have this retroflexion of the boundary current, and it throws off these anticyclones into the southern Atlantic. This is an anticyclone that's forming in an area where you have very high concentrations of floating tracers because you had river runoff of, say, microplastics. And in these boundary areas, these anticyclones will actually hoover up this floating tracer, and then they'll move into the interior ocean and start to expel it. And this has the potential to be a very strong transport pathway that might not be included in many of these studies of the transport of these materials, where they're looking at temporally averaged, low spatial resolution, large scale convergent currents. So just quickly to look a little bit at, so as I mentioned before, we have this V, which is an inertial particle velocity, which is a sum of the fluid velocity and this correction due to inertial effects, which is related to the Coriolis force due to the geostrophic scaling. And what we can actually see is the inertial effects can be characterized by a dimensionless number, the Stokes number, and the strength of the ageostrophic divergence can be characterized with a Rossby number. And we actually find that the two divergences, the two clustering processes, are comparable when we have this relation that the Stokes number is about the Rossby number squared. And this actually covers a pretty large class of material that could be of interest. So anything with a radius from 10 centimeters to 1 meter may lay in this regime. And that's particularly relevant because if we're thinking about like Lagrangian drifters, these Lagrangian drifters are more and more being used to measure divergences in ocean currents. And there's kind of a question of, are these divergences that are being observed, are they inertial or are they actually part of the ocean currents? So then what we really want to look at is how do these competing clustering processes, how do they interact and which one is really more important? So on the right hand here, what we can do is we can choose a Stokes number that balances the Rossby number we've observed in the quasi-geostrophic simulation. And then we can look at, so this is on the left-hand side is the passive tracer for a coherent vortex, the passive tracer concentration. And then we have light particles, which are less dense than water, and heavy particles, which are heavier than water. And we can sort of see that the light particles enhance this ageostrophic clustering, and the heavy particles sort of resist the ageostrophic clustering. And that's very different to what's reported if you consider these inertial effects in just the geostrophic velocity alone. Yeah, so I think that's everything I wanted to talk about. Thank you so much for coming, and thank you so much for listening, giving me the chance to talk. I really appreciate it.
Okay, now we can applaud him. Yeah, I had to unmute the microphones here first. Yeah, thank you very much for the nice presentation. Do we have questions from the audience here? I don't see much. Let's see what we have in Zoom. Javier?
Yeah, I have a quick observation. Well, actually, do you know about observations more than I do?
I've looked into observations, so I'm quite familiar with, but maybe sort of, yeah. I think for the we're kind of interested in clustering on like the sub mesoscale and then like the lower boundary of the mesoscale, which I feel like for most things like microplastics or whatever, we don't really have observations on that scale yet, I don't think.
Because the only observation that I'm aware of is this work by Eric Van Seville on microplastics, and they survey vortices, and they found accumulation on anticyclones, actually. And the theory that you're referring to is the first of a series of, how this has been evolved, but the most recent theory of motion of floating stuff actually predicts accumulation in anticyclones and repulsion away from cyclones. This 2015 thing that you're referring to is for particles that are immersed in the flow of a fluid. At that time, okay, we use it, but it's actually more applicable to things that are submerged, like floats. But yeah. Floats are different things, are cylinders. So, the theory has to be adapted.
Yeah, I guess, yeah, there's this sort of different is actually exactly at the surface and is exposed to both air and ocean currents, right? Versus so observations of microplastics. So I'm very interested in microplastics in particular. They're sort of distributed through the water column. They're not just at the surface itself. So they actually are immersed in the fluid. So that's a slightly different application to say the larger scale flotsam, where it kind of is impacted by, it has this windage effect that we're not considering. And so there are other simulation studies where they observe this clustering on cyclones and formation on anticyclones, and that's very much a similar kind of setting where you have immersed particles. So our results are sort of consistent with those.
One quick observation in the equation that you showed is delta -1 unless you have redefined delta.
Oh yeah. I think I've redefined delta. Yeah, it's definitely delta -1. There's kind of some in some of the work I've been doing, I've been using R, so slightly different to delta. Like it's just sort of just constants, right?
Okay, Igor.
My study. A quick question: have you explored the regime of large Rossby numbers? What happens when ageostrophic velocities become comparable and actually larger than geostrophic ones? Some kind of sub-mesoscale, small-scale regime.
I'm sorry, I think I missed the start of your question. I had a bit of
Okay,
internet
so
instability.
of course, have you explored the regime of large Rossby numbers when ageostrophic velocities become comparable or larger than geostrophic ones?
This is something like you can consider in the kinematic models very easily, but for the simulations we've been doing, obviously we can't explore that regime in QG.
I understand, but
Yeah,
have you?
that's definitely. I mean, I think the nature of the clustering process is quite similar in the two different regimes. The addition of because of course the solenoidal velocity field doesn't impact the size of concentration contrast. It only mixes the spatial gradients of concentration. So the actual relative size of the ageostrophic divergence isn't too important. It's more just about the fact that it's there. For instance, when they did this work with the biogeochemical models, we actually found that the inclusion of a divergent ageostrophic velocity, it was sort of a binary choice. It was basically, if you turned on this ageostrophic velocity, you observed completely different dynamics. It had nothing to do with like the relative strength at all.
Well, are geostrophic velocities important?
I think they're definitely important. Yeah, we're moving towards the submesoscale. I think the only difference is these weaker ageostrophic divergences at the larger scales. They're probably more important for the heterogeneity that we see at the larger scales because they have larger scales. But then, if you want to predict the variability at the submesoscales, then you need to consider the submesoscale ageostrophic velocities. Sure, they're definitely important.
Thank you.
Thanks.
Arthur?
Really enjoyed your seminar. Thank you for taking the time out to give it to us. It was very good. My question, actually, part of my question you already answered with Igor's question. So let me expand it a little bit. So this is very nice work on the free solution for two-dimensional turbulence, which has appropriate mesoscale, large scale consequences. Now, when we get to the real world, we have the force solution, as you mentioned, the Ekman and local wind forcing, which is when you look at satellite images and images of oil slicks and stuff, is very important. Then at the largest scales, we see a lot of filamentation along western boundary currents, for example. And when you look at the oil images, you see an extreme amount of filamentation at scales much smaller than the Rossby radius of deformation. And I'm curious if you thought about the interaction of all of these different processes, free solutions, force solutions, and the different scales of motion, which all affect particles in the ocean.
Yeah, it's definitely something because so the kind of way we see it is we're like building complexity into these models. We start with the kinematic, we move to the quasigeostrophic, maybe then we move to primitive equations, maybe then we have some kind of forcing. And it's obvious that all these things are really important in the observations. But in terms of yes, it's hard for us to answer at this stage what the relative importance of all these different things is, but obviously we expect, particularly the Ekman, it seems like the Ekman currents determine the global distribution of these things very strongly. And that's a lot of what we're interested in. It's sort of like what we're interested in is when you ignore these smaller scale sources of heterogeneity, what does that mean for the total transport? So because I have mentioned a few times this whole thing of eddy diffusivity, this whole thing of parametrizing the mesoscales and how that reduces the upgradient transport. So, for instance, even if we had a global model, but one that was eddy resolving, would we see a much greater transport due to these sort of eddy pumping effects and these mesoscale ageostrophic velocities that wouldn't be seen otherwise? Yeah.
Yeah, I also think, yeah, it's also strongly sub-mesoscale. The results are very nice for vortex-dominated systems, but a lot of satellite imagery shows an extreme amount of energy at the smallest scale in terms of filamentations and filaments.
Yeah, I think another like idealized system that we may be able to look at next is we have lots of ways to generate these gyre solutions, and then we can sort of look at the interaction of the boundary current and clustering, which obviously we can't have in this homogeneous turbulent fluid.
Very nice
Okay,
work. Looking forward to seeing your future work. Thank you again.
Thank you.
We have a question from John Van Leer here in the room.
Yeah, thank you for the presentation. I would like to draw your attention to two things. You spoke in your talk about observations in kind of a blurred way, as though observations of things from a model are equivalent to things from the actual world. And my view as an old-fashioned observationalist, an observation is something that comes from the atmosphere or the ocean or some physical place like that, whereas the characteristics of particles in a simulation can't be really called observations. They are, characteristics of a model. A second item, many of your figures rely on color to convey their points, and when you're colorblind, you're colorblind.
Yeah, and in addition to that, our projector here is really a little old and doesn't show these colors very well. So some figures look just like dark rectangles, but that's not your fault. Any responses to John?
Yeah, that's totally fair. I mean, I'm probably being a bit inaccurate with my language referring to observations. When I was first referring to observations, I was referring to things like ocean color measurements and these kind of trawling studies. It wasn't just numerical models, but then I probably did use and then I'm very sorry if you were having problems with seeing my plot zone. That's my fault. I tried to use perceptually uniform color maps and things. Maybe it wasn't coming through on the projector very well, or maybe I've incorrectly used the wrong color maps. Yeah, I'm sorry about that. I'll look into it.
He cannot hear you. I have to come closer again.
If you can use symbols rather than colors, then everybody can see them.
Okay, sure. I'll make sure to do that in future.
Okay, I don't see any further questions here or in Zoom, so I say thank you again for the nice presentation. Maybe next time you can come in person or we meet you at some conference. Thank you all for coming. We continue on Friday with the next OCE faculty candidate on what did I say? On Monday morning. And then Wednesday, Lillian Henderson. And next Friday, we have student seminars again. And don't miss Michael's cake outside. When you go back, he brought a very nice cake. Okay, thank you and goodbye.